So what we learned previously in 3.2 and then spent all last class doing with our unit circle paper plates that we built was knowing that an angle in standard position on a circle with radius r centered at the origin, there was all these points P that we wrote around our unit circle where the end of our circle intersected with those angular lines, the terminal ray. So we have all of these points around our circle. And I told you last time that they're cosine, comma, sine. Great. If we apply this beyond the 1 unit circle, meaning we're going to put back the radius. Radius will not always be 1. We have the following problem, is that we don't have a coordinate point right now that represents the actual coordinate point except for when the radius is 1. So what we can do is we can take the definitions of cosine and sine, which is horizontal displacement over radius and vertical displacement over radius. And we can multiply both sides by r so that it's solved for x and it's solved for y. Highlight with me here. Let's say we have these two coordinate points, x equal to r cosine of theta and y equal to r sine of theta. So our coordinate points go from just being cosine, comma, sine, which is from the unit circle, radius equal to 1, to being r times cosine of theta, comma, r times sine of theta. It's really the same thing. It's just that last class our radius was 1. And multiplying by 1 is boring. It doesn't do anything. It's the identity. So it doesn't change cosine and sine. But today I'm going to change the radius length that we're using on these circles, so it will change the coordinate points. And all you have to do is multiply by the radius. So if we add this color scheme to our unit circle, or our picture of a circle here, we have our radius, which is the length that you're going to see of the radius in all of these positions. The radius length of that terminal ray, the radius shown on 0 angle. And then we can highlight, just like we did before, our cosine of theta and our sine of theta. They are still x and y. We're just now multiplying by that radius. It's pink. Example 1 says, the figure shows a circle centered at the origin with an angle of measure theta in standard position. First things first, let's make sure we understand what we're looking at. This is the angle theta, which means this is my terminal ray. We're looking at that angle right there. The terminal ray of the angle intersects the circle at point P, which means we want to find the values of sine, cosine, and tangent. This is an intro level. This is exactly what you just did in Quiz Trade, because this has a radius of how long? 1. So this is a unit circle. We know from what we did last class and Quiz Trade that the sine of theta is going to be what value? Y. So in this coordinate point for P, it's square root 3 over 2. Which means cosine of theta is going to be what? 1/2. Now let's see if we remember this. What do we do for tangent? Y over x. So we'll do our math again, even though I know it's on the back of your unit circle. This is going to be square root 3 over 2 divided by 1/2. What was the rule for dividing fractions? Keep, change, flip. So we keep, we change, we flip. What is this reduced to? Square root of 3. Awesome. Easy. Next point, or next question, you're using the same picture. It says the point R is the result after point P is reflected over the y-axis. Let's do that. If we take the point P and we reflect it over the y-axis, that means we're reflecting it, boop, over here. So boom, we have our new terminal ray because it's hitting point R. If it's reflected over the y-axis, what's the new coordinate point for R? Instead of going to the right and up to get to point P, what did we do? We went left and up, which means my coordinate point is going to be what? Negative 1/2, comma. Fabulous. That is a weird looking 3. Let me try that again. Square root of 3. Still weird. Whatever. You get it. Okay. Now, it says let alpha, this is the Greek letter alpha, let alpha be the angle in standard position whose terminal ray intersects to the circle above, okay, it's on the left, at point R. So now we have a new terminal ray that comes from the vertex wow, that is not a straight line, and hits point R. The angle alpha is the angle that goes from the positive x-axis all the way here to the line that hits R. That's our angle alpha. This time we're going to find the sine, cosine, and tangent of alpha. Since we know the coordinate point R, what's the sine of alpha? Look at the coordinate point. Square root 3 over 2. What is the cosine of alpha? Negative 1/2. And since we know we are in quadrant 2, let's not work harder, let's work smarter. We know in quadrant 1, the tangent of that angle, same reference angle, was positive square root 3. We're in quadrant 2. What will tangent be? Because in quadrant 1, what is the only trig function that is positive? In quadrant 2 is the S quadrant, sine. Very good. So again, this is just using your unit circle so that you have it solidified on your notes. Since last class we didn't take actual notes, we just built that unit circle. Now you see an example of using it so you can look back. But let's make this a little bit more challenging, shall we? We shall. The example 3 says the figure on the left shows a circle with radius 4. Ooh, important. What's the radius length here? 4, along with the equilateral triangle PQO. We're going to determine the coordinate points of point Q. Interesting. Let's talk about equilateral triangles for a second. And because I know questions I'm going to ask you later, we'll also talk about an isosceles right triangle. What are some things you know about an equilateral triangle? All sides are equal. Okay, so let's draw ourselves a little picture. Do the best you can. Oh, that was actually a good triangle for me. Shout out. But to make sure that you know that they're all equal length, we're going to put the little tick marks on all the sides to show that they are equal in length. Since they're all equal in length, what else is all equal? The angles. Very good. So let's put the angle arc marks so that show that these are all the same. Now question, if they're all the same angle, what angle are they? 60 degrees. Ooh, but we're not using degrees. So in radians, how much is 60 degrees? It's your green lines. Pi over 3. So we're going to put pi over 3 in every single corner here, because every single one of these angles measures pi over 3. Those are things we need to know about equilateral triangles. Now we'll go to isosceles right triangles. What are some things you know about isosceles right triangles? 2 equal sides. What else? What's one of the angles going to be? 90 degrees. Okay, so if we're drawing one of these, again, just do your best to make it a right triangle. Okay, actually not that bad for me. But since it's a right triangle, we're going to put the symbol for a right angle in the obvious corner. And like you guys said, isosceles have 2 equal sides, so we're going to mark 2 of the sides as the same and the third as different. Now we need the angle measurements here. You guys already told me that the right angle is how many degrees? Which is what in radians? Pi over 2. Very good. So we have pi over 2 radians in this corner, which means how many radians do we have left to give to the other 2 angles? 90 degrees or pi over 2 again. But since these angles are across from sides that are the same length, there's a rule with isosceles right triangles that makes those angles the same. 45 degrees, what is that in radians? Pi over 4. Very good. All right, we know things about triangle. We listened in geometry class. Love to hear it. Shh, don't tell on yourselves. Okay, so here this question then says, because we're going to use that knowledge. The figure on the left shows a circle with radius 4. Check, we saw radius 4, along with this equilateral triangle. Let's fill in some things we know about the equilateral triangle, specifically with the angles. How much is this angle worth? Okay, sorry, I drew that really poorly. How much is this angle worth? Pi over 3, because that is an equilateral triangle. So that means this whole thing is pi over 3. All of these are also pi over 3, which are not that important or exciting for me. So my question is, if we're trying to get to point Q, my angle will actually go from the positive x-axis all the way here. if the little bit in the middle is pi over 3, how much is this part? Also pi over 3. So that means that my angle had to travel how far angularly to get to the Q line? 2 pi's over 3, because we went pi over 3 to reach this line, and pi over 3 again to reach the Q line. So my angle that we're using here is going to be 2 pi over 3. That's theta. All right, so here's the things we know. We're just going to list them out so this is helpful later. We know that the theta of my angle that goes to point Q is 2 pi's over 3. We also know that the radius is how much? 4. So the coordinate of point Q is made by doing r cosine of theta, comma r sine of theta. We just got to fill some stuff in. We're not even going to evaluate the sine and cosine. We're literally just going to fill this in. So Q is going to be 4 times the cosine of my angle theta, which was 2 pi over 3, comma 4 times the sine of 2 pi over 3. Couple of notes, these parentheses around the angle as if it's inside the cosine are not technically required unless it's unclear that it's plugged in. Meaning if it's a negative angle, you will need to put it in parentheses. Positive angles technically don't, but I like doing it for the most part because it's clear to my brain that it's inside the cosine function or inside the sine function. Mathematician's choice on that until it's negative, in which case we need it. Are there any questions about this? How we got this point? Fabulous. We don't have to. You can. Since we do know the values of cosine 2 pi over 3 and sine 2 pi over 3, you can evaluate this further, but for today we're going to leave it like this. Because it's just one more step away to evaluate those functions and multiply by 4. But I'm so glad you asked that question. Yeah. Because example 4 is going to need us to think about the evaluation of these functions. So it says the figure on the right shows a circle of radius r along the line y equal to negative x. I've got to zoom out further to see this. So here's our negative sloped line, slope of 1, going through the origin, classic linear function. The circle on the line y equal to negative x intersects at the point R, O, and P. If the coordinates of point P are 6 square root 2, comma negative 6 square root 2, what is the value of R? Interesting. Here's what we know. We know that the value of P is 6 square root 2, comma negative 6 square root 2. And we also know that these coordinate points can be created by r sine of cosine of theta, r sine of theta. So we need to see a value that would make sense for the evaluated version of sine and cosine. So let's look at our unit circle for a second. Do you see any of the values around your unit circle that involve the square root 2? Because that looks peculiar to me. Yeah. What does it say in the coordinate point? So if you're looking at where pi over 4 meets your unit circle, what is that coordinate point? Comma. Okay, great. So I realized that the square root 2's should normally be divided by 2. Yes? Okay. Well, if we want to divide these square roots by 2, without changing the actual number, what do I have to change this number to? So that it still eventually becomes 6. Okay, I want to put a number right here so that when I divide by 2, I get 6. 12. Sorry, I did not hear you if you said it. Say it with confidence. And same thing over here. If I have square root 2 over 2, that would be like there's a 12 right here. Now, if we think about our coordinate point, we know that it's r cosine of theta, r sine of theta, which means this is really 12 times the cosine of some multiple of pi over 2. Wait a second, which quadrant are we in if we have a positive and then a negative? Positive and then a negative? Quadrant 4. What is the multiple of pi over 4 in quadrant 4? 7 pi over 4. And then we're going to do comma 12 sine of 7 pi over 4. A question I expect you to ask me, why did the negative go away? Thank you for asking. On your unit circle, what does it say for sine of 7 pi over 4? Is it a positive or a negative number? So a negative number times 12 would be negative 12, yes? That's why the negative went away, because in that quadrant, sine itself is negative. So really cool. Okay, great. We've done all this work. The question was, what's the value of r? What is the radius here? 12. So we had to solve this to where we saw cosine and sine, or values of cosine and sine, in my coordinate point. The number in front of it is your radius. Basically, these are becoming math facts I'm going to need us to know. To recognize that square root 2 should always be divided by 2 to come out of my unit circle. That's going to be something we need to recognize, and then we make the puzzle match after that. Ari, you were about to ask a question.
No, it's okay.
Okay, are you sure? Okay, fab. Let's flip the page. Based from here on out, what I'm going to do is have things that maybe help you memorize the important values around your unit circle. The first thing is called the hand trick for quadrant 1 trig. And then I know on your quiz trade cards you saw the hand trick written there. Let's actually learn what it is. I have a separate video, by the way, on YouTube. I refilmed it yesterday because I filmed the first one in like 2021 and I got nervous that my hand looked funky. So there is a video on my YouTube channel where you can see my hand to do this. So if you forget what I've done just now in class, that'll be that. I can't show you everything all at once, so on your screen I'm going to show you this part, but you're going to look at both pieces. This is the pattern of the hand trick that we will need to remember so that we can do all of our quadrant 1 trig with only our hand and not a unit circle. So if you're like, what? Go watch the video on YouTube because I walk through how to do it again so you can see my fingers. But live in class. All right, how do we feel after practicing the hand trick? Are we okay? Yeah. Remember, if you want extra tutoring with this, I do have a video online that shows, because I recorded it underneath the little document camera so you can see my hand. Don't judge all the lines on my hands. I got really nervous about it. Never know how many lines are on your hand until you're just looking at it on a computer screen. Anyways, we can do all of the quadrant 1 trig, which then extends to the other quadrants with our left hand. One thing I want to add to this page before we go on is the color scheme we've been using from our unit circle. Pi over 3 has always been the green line, if that's helpful for you. Pi over 4 is the pink line, and pi over 6 is the blue line. So we are doing all of these values from your unit circle. There's the same color scheme, so it all looks the same. And in fact, on the whole next page, if you flip your paper over, what have I provided for you? Another copy of the unit circle in case you lose your paper plate. Let me answer the phone, 1 sec. All right, let's add our color scheme to this unit circle so that we can follow the same color scheme. We'll start with the pink lines. Whoa, calm it down, everybody. We'll start with the pink lines, which is all of our over 4s. Those are halfway in between our quadrants, since it's halfway between 0 and pi over 2. So we have our color scheme. Who knew markers would be so dramatic? This squad right here. So crazy. Our pi over 3 lines, which if you follow all the lines that have been labeled with an over 3 angle, are green, to follow our color scheme from before. And then the pi over 6s and all the multiples of pi over 6 that don't reduce to a pi over 3 multiple are the blue one. Now you not only have your paper plate unit circle, but if somehow that gets lost or you weren't here last class, you now have a unit circle completely filled out that you can then put on your paper plate or use this guy. But there's another way to memorize the values around the unit circle that may be more helpful for you. This is one of those things where if you're really good at test taking, where you like open the test and then like brain dump, this might be something nice to do. For the AP test, you can't use the same piece of paper throughout the entire thing. Like, you will have to turn in your scratch paper with each section, which means you do this every time. Up to you. That's why I recommend actually memorizing it with the hand trick. But this table that you see at the bottom is going to be on every formula quiz from here on out. I'm going to ask for the values of sine, cosine, and tangent for all the quadrant 1 angles. Yes?
Is that all the quiz? Like just that table? That's the whole
Oh, no, there's more stuff on the quiz. But I'm only going to ask quadrant 1 on your quizzes for now. But here's how to make this table easy. We're going to start in the centers. In the center, we have pi over 6, pi over 4, pi over 3. Watch what happens when I write down the values of sine in that order. I'm skipping 0 and I'm skipping pi over 2 for right now. We have 1/2, sorry. We have square root 2 over 2. We have square root 3 over 2. What are some things you notice about that? 1, 2, 3. What are they all divided by? 2. Technically, they're all square rooted, but the square root of 1 you can do. Square root of 1 is 1. Boom. Okay, can we memorize that? If you forget how to memorize it, you just did the hand trick to learn how to find it, so we're good. Let's do cosine. Watch this. Square root of 3 over 2, square root of 2 over 2, 1 over 2. What do you notice? It's going backwards. 3, 2, 1. All divided by what? 2. Tangent is sine divided by cosine. And since we know we keep change flip and end up canceling out the 2's every time, here's what you can do. Sine divided by cosine. Oop, we can't leave our answer like that. It's square root 3 over 3. Sine over cosine. What's square root of 2 over square root of 2? Then if we do sine over cosine, it's square root 3 over 1, but dividing by 1 is boring. Instead, what could we write there? Square root 3. Look at that. 9 out of the 15 boxes. 1, 2, 3, 3, 2, 1. And then you have the answers. Sine divided by cosine. Sine divided by cosine. Sine divided by cosine. For 0 and pi over 2, we do need to know this one, so we'll think about our hand trick again. Put your pinky down for 0. Sine is below. How many fingers are below? When the numerator is 0, it's 0. For cosine, how many fingers are above? 4, but we're doing square roots. So what's the square root of 4? 2 divided by 2 is? Tangent is sine divided by cosine. What is 0 divided by 1? 0. What do you notice about that column? 0, 1, 0. Nice. It's binary. Yeah. Let's do pi over 2. So put your thumb down. Pi over 2 is your thumb. How many fingers below? So square root of 4 is? Divide by 2 is? How many fingers above? If we do sine divided by cosine, what is 1 divided by 0? Oh? Oh my gosh, can we divide by 0? It is undefined. It's not a trick question.
I broke math.
I broke math. So here, we already now have 3 ways to memorize. You can look and if you're a visual thinker, think about your unit circle. If you're a manipulating person, that sounds weird. Let me say that differently. If you like to use manipulatives, what word am I thinking of? If you're a tactile learner, you have your hand for the hand trick. If you like patterns, visual. Thank you so much. Why was that so hard?
But this is why you're good at math.
It's Friday.
Oh, you're good at math.
I am.
English might not be your forte.
Thank you so much. I needed that. All right. What were we talking about? Oh, the third way is the table. Again, the table is maybe the least helpful on the AP test because you have to write the table every section. There are 4 sections. But if that's the way you learn, that's the way you learn. I will ask you for the values in the shape of this table pretty much on every formula quiz for the rest of the quarter. If you remember the pattern, great. If you use your hand to figure it out every time, you can't use your unit circle on your quizzes. I know. Questions, comments, concerns? Today, the main idea was extending our unit circle to include radii that are not 1. So it's just r cosine theta, comma, r sine of theta. Second part of today was continuing to memorize and use the values of sine, cosine, and tangent. To practice, I'm going to have us play a gim kit. This gim kit is going to extend beyond quadrant 1. I would challenge you to try to start to do this without your unit circle, but obviously we're learning. So if you want this first time to play with your unit circle in your hand, you can. I'm going to eventually ask you to do this all without a resource. Okay? Yes? Great. Awesome. Let's play.